Thanks again for the introduction. So for everybody who is here this morning, we're going to see another example that's not clustering of nonparametric Bayesian methods. And in general, what I'll be talking about today is how many of the most popular probabilistic models for graphs are misspecified in that they generate too many edges, more edges than we expect in a lot of realistic scenarios. And so what can we do about that? How can we create a new framework that lets us actually have sort of correctly specified graphs, sparse graphs? I'll mention a few things. So one, my lab actually works on a variety of problems in scalable Bayesian inference from a very practical side, an algorithmic side, a modeling side, all the way over to a theoretical side. And so I actually gave a couple of options for talks for this, and Alex went with the theoretical one. So I just want to give you a heads up that we also do much more practical things than you'll see in this talk, although I do think this has very practical implications. And so I'd be interested to talk about that with you in future as well. So this work is with an awesome graduate student, Diana Kai, and an awesome postdoc, Trevor Campbell. Trevor's over here, and he'll be participating in the discussion later. And we're both, generally around. We're just across the street, and definitely happy to chat. Okay, so this talk I'll be focusing on graph data. So in general, we're thinking about big data. We have a lot of graph data, and not only are we getting, sort of more graph data all the time from different areas like social networks, biological data, transportation data, but in fact, those graphs are often growing. More people are joining a social network. They're sending more messages between each other on a social network, and we want to capture those dynamics, those growing dynamics, as well as just the fact that we have a lot of data. And so in general, I'm interested in probabilistic models for graphs, as many people are, for the same reason that you might be interested in probabilistic models in any other sort of application area. So in particular, we get rich relationships in our data. And by rich relationships, I don't just mean nodes connecting in a graph. I mean deeper things. We might have a collection of graphs. Maybe in different countries, there are different transportation graphs, and we want to share information, share power across inference in those different graphs. Maybe we have different parts of a graph and we want to share power across those different parts of a graph. We get coherent estimates of uncertainties, and so if there's some parameter, some sort of deep set of knowledge in the graph that we want to learn about, we don't just learn some estimate for that parameter, we get a sense of how certain we are about that estimate by using probabilistic methods. And if we have any prior information, we can encode that in our model as well. So these are reasons to take a probabilistic approach, and there have been many probabilistic approaches to learning graphs. So the stochastic block model, the mixed membership stochastic block model, this isn't even the tip of the iceberg. I'll direct you to this 2012 overview, but of course there have been many graph models even since 2012. I'm just not listing them all here. But this has been a huge area. A lot of work has been done. And here's the interesting thing though. So if I said in the beginning, we're interested not just in graphs, but in growing graphs, and we want to learn in graphs that are actually growing over time, maybe we're getting some streaming data, we might make some very basic assumptions here. So I think one very basic assumption we might make is projectivity. That as we add more data, that doesn't change anything about the previous data. So when we were talking about clustering this morning, you can imagine that as you get more data, you don't think that the assignments of data points to clusters for previous data should really change. And so here we might think of our graph as maybe being emails between different individuals. Maybe we're analyzing some Enron email data set. And we think that as you observe more emails over some weeks, you don't think that should change the distribution of the previous emails. It shouldn't change whether somebody sent an email 2 weeks ago. So this is sort of a very basic assumption, this projectivity assumption. But here's the kicker. If we assume projectivity, then all of these models, and the many, many, many other models that I didn't bother to write up here, but definitely exist and have been very influential, are misspecified in the sense that they generate dense graphs, graphs that have too many edges for certain types of applications. And so this is problematic. I mean, if we want a model that actually accords with our data, that gets the right sort of behavior in our graphs, then we can't use this framework. We can't use these models. We need to come up with something new that will actually let us get correctly specified graphs. And so what I will be talking about today is a new framework that actually lets us get sparse graphs, graphs that have fewer edges in a way that I'll make precise shortly. So in the remainder of the talk, I'll first start by talking about this model misspecification problem, what goes wrong, how do I know that it's happening for all of these models at the same time. what is a dense graph for that matter. And then I'll talk about our new framework for sparse graphs and talk about how we show that in fact it does generate sparse graphs. And I'll mention that this has been an exciting area of research recently with a lot of interest. And so a lot of the ideas and development I'll be talking about today is actually concurrent and independent work with some cool work by Crane and Dempsey. And so I'll encourage you to check that out as well. Okay, so we're thinking about graphs. And as I said, we're not thinking about just a single graph. We're actually thinking about growing graphs. And so instead of just writing a single graph, we're imagining that we have a sequence. So we have our first graph, our second graph, our third graph, and so on. And at each step in the sequence, we can imagine that we might be adding some vertices, we might be adding some edges, we might be adding some vertices and some edges. But in general, we have this sequence where things are growing. And it goes off to infinity. We imagine that, in fact, there are a countable infinity of steps in this sequence. And now, if we also imagine that as this sequence goes to infinity, the number of nodes in the graphs goes to infinity, then we can define what it means to be a dense graph and a sparse graph. It's actually a property of the sequence, more so than the individual graph here. So we'll say that we have a dense graph sequence if the number of edges is at least quadratic in the number of nodes. And so to see why this would be problematic, we'll think about what happens with a complete graph. If I have every node connected to every other node, and the number of nodes is n, then I have n choose 2 edges, and that is quadratic growth in the number of edges. And so here we're saying essentially that things kind of behave like a complete graph, and that might not be realistic for certain types of applications. You know, if you think about even a social network, you know, not everybody is connected with sort of a fixed proportion of everybody else, or you know, even some significant proportion. Usually you just sort of know the people that you know, and it's kind of small. And so instead, we might be interested in modeling sparse graph sequences that have strictly sub-quadratic growth in the number of nodes. Now, in fact, in real life, we're actually interested in particular types of sub-quadratic growth. Maybe a power law, maybe n log n growth, maybe even linear growth. But here I'm just taking the weakest possible definition. We're saying, hey, we don't like this quadratic growth. Let's try to even get sub-quadratic growth. And we're going to find that even that is hard in the existing framework. Okay, so what is this existing framework? What are these existing models doing wrong so that they're not able to get even this very weak definition of sparsity? Well, in the framework that these models belong to, we have a very specific type of graph sequence that we're building up. In particular, at each step in the graph sequence, we add exactly one node. So in that case, we can sort of just label each node by the step that it's added because we're only adding one node at each step. So the first node on the first step is labeled the first node. Then we get the second node on the second step. We get the third node on the third step, and so on. And the way that edges are added in this framework is we imagine that at each step, all possible edges, or all edges that we'll ever have between a node and the nodes we've previously seen are added. And so what this means is we have this edge between 1 and 2, and we'll always have it going forward. We don't have an edge between 3 and 2, and we'll never have it going forward. And then we do this for step 4, we do this for step 5, and we just imagine that this just keeps going off into a countable infinity. Now again, we're taking this probabilistic approach. We're thinking, what sorts of distributions can we actually have over not only these graphs, but graph sequences here. And so we want to ask ourselves, well, what sort of properties would be natural for these distributions? And a natural property that people have identified in the past is to say that let's put a distribution over this sequence, and let's assume a very natural form of invariance called exchangeability. What exchangeability means in this framework is that if I take any step of the graph sequence out and I look at the probability of the graph in that step, so I take this step out, I look at the probability of the graph in that step, I say that it wouldn't have changed if I had seen the nodes in a different order. So a way to think about this is, maybe these are people joining a social network, and maybe they had joined in a different order, or maybe these are people in a social network, and I just observed it later, and I said, hey, I don't know the difference between Alice and Bob and these other two people, and so I could have just renamed them, and I don't think that that should change too much. Okay, so this is an assumption, sort of invariance assumption we could make on probability distributions over graphs. And it's one that dates back until around the 80s with the work of Aldous and Hoover at least. And we're going to just make one small change and call this node exchangeability to emphasize that the things we're exchanging are the nodes. Yeah?
You said two things that sound similar, but I'm not convinced that they're the same. So the Alice and Bob thing I totally get. Like, if you just have random labels on your nodes that are just their names,
yeah.
then I understand why you would say, I don't know Alice, I don't know Bob, whatever. It could be Alice, could be Bob, could be Bob, could be Alice. But when you're talking about the order, I'm not sure I understand why the order of the nodes is that when you look at a process that is growing. I mean, so
one way to think about this.
I look at a tree and I can't say to myself, well, maybe the leaves first grew and then the trunk came later. Like, it's very clear.
Yeah.
In a tree, what came first.
So in this, one way to equate these in your mind is that a way that we could represent this graph in general is an adjacency matrix. And so what I'm saying is that if I permute if the rows and columns represent essentially the same nodes here, if I permute them in the same way, that this shouldn't change the distribution of the graph. So implicitly, there's an order just because I was putting Alice before Bob in that matrix. And so that defines an order in exactly this sense that I described before. It doesn't have to be a time order, but that's certainly one way that you could choose to interpret it. But there is an order, and that's the order that we're permuting.
Is it like you are changing the order of Alice versus Bob, or you are just relabeling them? Like, are they like exchangeable on isomorphic graphs, or just like the order you are putting? Because it looks like you have renamed like 2 to 4 and 3 to 1.
So if you assume that every label is associated with an integer, which you can always do because there's a countable collection of labels, then that implicitly gives you an order, because Alice was either 1 before, or now she's 2. And so in that sense, you have an order. It doesn't necessarily have to be interpreted in a time sense, but you do have an order, and that's the order that's being permuted. Yeah?
To understand what you're saying, it seems like then a tree, if you think of a tree as representing a process over time, like an evolutionary tree or something like that, that would not fall into this category, right?
So yeah, so I think one thing that's worth thinking about is that yeah, so there are definitely types of graphs that you would not have this type of exchangeability for. So it's more like this is a type of invariance property that you could be interested in, and it's definitely not one that you have to be interested in. Another reason that you might not be interested in this invariance property is that you think there are fundamentally different time dynamics in the graph. And so then you wouldn't think that the labeling process that goes on maybe at time 17 is the same as the labeling process at time 1. You might think that there might be fundamentally different dynamics. Another way that exchangeability comes up and is used quite often for typical data, so not graph-aligned data, but if I just have like vector sequences, is I say, hey, these vector sequences represent maybe pixels and images that I downloaded from the internet. If I had downloaded them in a different order, I don't think that should matter. Now, conversely, if these pixel sequences represent, my robot is moving around the world and it's actually going into a fundamentally different area, and I don't think that's exchangeable with what I did before, and I actually know in advance maybe even that it's going to spend some time at the Broad and then it's going to spend some time at this data center, then I would maybe have exchangeability in those separate areas, but I wouldn't have it overall. So there's definitely a lot built into this assumption, and that's worth thinking about, and in fact, we're going to see in a moment some of the implications of that. It doesn't have to be that every possible distribution you could have over this would exhibit exchangeability. It's an assumption on distributions. It definitely restricts your distributions. But nonetheless, the reason we care about this is it's a very popular assumption to put on distributions, especially distributions over graphs. So I would say not necessarily over trees. I wouldn't say that this had been used extensively in trees, but in general over graph processes, perhaps to model something like a social network. Okay, so in fact, Aldous-Hoover studied this around 1980 and characterized it in order to get a sense, again, of what goes wrong with this in terms of generating too many or too few edges, this idea of density or sparsity. Let's look at an example of something that would generate an a node exchangeable graph sequence. So here I have the unit square, so 0 to 1 in both directions, and I'm going to put down a function on the unit square. So W takes its first argument as the horizontal direction, its second argument is the vertical direction. W is potentially some really interesting function. I drew a boring one because it was very easy to draw. Maybe this is a high value over here, and that's a low value at the lighter value. W is always valued between 0 and 1. It could also be a random function. And so here I've drawn perhaps a particular realization of W, but in general, it could be totally random. It's also symmetric, and so that's why I didn't bother to draw it below x equals y. I only drew it above x equals y. It's symmetric around x equals y. Okay, so here's the way that I'm going to draw my exchangeable graph, or a graph for the moment. I'm going to draw a uniform random variable between 0 and 1. Totally independent of w. So w might be random, so this is going to be an independent uniform random variable. And I've only drawn one uniform random variable. I just happen to plot it twice. I plotted it on the vertical axis as well. And for every single node, I'm going to draw this uniform random variable independently. So for the second node, I'm going to do the same thing. I'm going to draw another IID, uniform random variable. And I'm going to look at where these two nodes' values intersect, and I'm going to say that's the potential edge that could exist. Now, this potential edge, I'll say, has probability of existing equal to w at that value, and that's a totally fine thing for me to say, because remember, the value of w is between 0 and 1, so we can interpret it as a probability. And finally, what I'm going to do is I'm going to make a Bernoulli coin flip with success probability equal to the probability at that value. So here, in this case, I make a Bernoulli coin flip with that success probability, and maybe it happens to be a success, and so I get an edge. Okay, so now I do this again. For the third node, I put down a uniform random variable between 0 and 1. I look at all the intersections. Those are the possible edges that I could have. I look at the probability of w at each one of those, and I make a conditionally independent, conditional on w, Bernoulli draw at each of those. And maybe in this case, they just both happen to be failures. So I don't get either edge. And I can keep doing this. For every one of these nodes, I can go up as many as I want. I can make this IID draw, this IID uniform random draw, and I'll see which edges I get and which ones I don't. And I think what should be straightforward to see at this point is that this is going to generate a node exchangeable graph. And the reason for that is every node corresponds to an IID uniform random variable independent from w. And if I permute any two IID uniform random variables, I'm not changing the distribution of the graph. Now, here's the reason that we're really looking at this example. Aldous and Hoover showed around 1980 that the converse is true, that every possible node exchangeable graph can be generated in this way, that there's this underlying w, this graphon structure that might be random, that when we take it and make these IID uniform random draws, independent of w, we get back the distribution of the graph. Okay, so why is this important? Well, again, we wanted to ask this question of why are all of these different models that are out there generating dense graphs? And this construction is going to let us answer that question. In particular, now that we have this construction, we can say, what's the expected number of edges in the graph? Well, there's n choose 2 possible edges after we've seen n vertices. The probability of the edge is this wxy, and then we integrate over the two uniform random variables in the x and y direction, and they're independent. Okay, well, n choose 2 behaves asymptotically, is asymptotically equivalent to some constant times n squared. And then the rest of this expectation doesn't depend on n. So in fact, this whole expectation depends asymptotically on n, like constant times n squared. And remember, n is just the number of nodes. And so we've got two choices at this point. Since w was strictly non-negative, c is strictly non-negative, so it's either 0 or it's positive. So either this is a dense graph because we have the quadratic growth, or it's empty, which is a particularly boring graph, so we pretty much only care about the dense case. And so this is amazing. Well, first of all, let me say, we just said something about the expectation here. You can make this stronger and make this a with probability 1 statement. And it's actually pretty straightforward to go from this statement to that. But this is pretty amazing. We showed that every, and by we I mean Aldous and Hoover, showed that every node exchangeable graph sequence is dense or empty almost surely. And so now it turns out that every one of those graphs that we saw in the beginning, every one of those models is node exchangeable. This is very easy to verify. So it must be dense or empty almost surely. And in fact, many, many models that haven't been created yet, you could also check if they're node exchangeable. They would also be dense or empty almost surely. And I'll just point out that Orbans and Roy called attention to this in a nice paper in 2015. Okay, so at this point, we sort of say to ourselves, ooh, this is maybe problematic. Oh, yes?
So should I think of this as a single W that's being reduced, or is there a selection?
So yeah, so for a graph, we would choose a single W. It's like we would draw from the distribution of W, and then we would have this result. And in general, this is like Di-Finetti mixing measures. So, so if you recall, we have this fact from some sort of exchangeability that if I have any exchangeable sequence of random variables, that there always exists some sort of underlying, we could think of it as a parameter, such that conditional on that parameter, which could be random, our data are IID. So we make a draw from that parameter, and then we draw our IID data. But that parameter will be shared across all of that data, and it's the same thing here.
And the parameter is the graph on it, the function W in this case.
Yeah, exactly.
So if I had sort of two W's I was switching between, one of them is split to dense things and one to empty things, but I have 50-50 chance of choosing. Then how do I think of the sequence of graphs depending on that?
So essentially you would have another, so if I understand your proposed model correctly, which would be that, you know, I maybe have some dense W and some sort of zero W, let's just say, and I actually have some underlying probability of choosing between them, and then I choose. So if the way that you choose your W is you first make that mixture choice, then you effectively have a new W, which is a mixture of the W's, and that would probably correspond to a dense W. Just with a lower constant. Oh, right. Oh, yeah, so, okay, yeah. So it depends on the probability and how you would choose them. But yeah, so you might have chosen an empty W, yeah. Okay, so another way to think about this is if we have this exchangeability assumption to a particular node, all of the other nodes kind of look the same. I mean, because that's exchangeability. And so we're saying, you know, okay, either I sort of don't connect with any of those nodes, or I connect with kind of a fraction of those nodes. And so that's what's going on here.
I have a question. How are you connecting between the values of W and one edge created? I mean, suppose the value of W is 0.1. So do you have a condition on the value of W or something like that?
So I mean, so this illustration is exactly how W connects to the probabilities of the edges. So we choose the W, we draw the W, and then we draw the edges conditional on W in this manner. So this is the construction. Okay, cool. So we'd like a framework that doesn't have this dependency, you know, that maybe allows sparse graphs. And so there are various things that we could do, but one thing that we might think is, well, what we just proposed was to exchange the nodes. There's basically one other thing in graphs, it's edges. Why don't we propose to exchange the edges instead? And I'll just mention there's a lot of work on, I think right now this is a very sort of interesting area that a lot of people are working on. And so there are certainly other approaches that one might take. But let's talk about this edge approach. So the edge approach is to say the following. So now instead of saying we're going to get one node at each step in the sequence, we're now going to say that we get one edge at each step in the sequence. So now we can label the edge by the step on which it occurs. So for instance, on the first step, we get the first edge. On the second step, we get the second edge. On the third step, we get the third edge, and so on. And just as we created nodes, or sorry, as we created edges associated with nodes before, now what we're going to do to create nodes is we say that they come in when the associated edge comes in. So a way to think about this is now these edges might represent emails, you know, maybe these are emails between people at Enron, and we'll see somebody enter the network when they send an email. So here, Alice and Bob are sending an email between each other. Here, Bob sends an email to Catherine, and so she comes into the network. Here, emails are just between people we've already seen, and here there's an email between two people we haven't seen before. And so we can imagine, again, that this generates an infinite graph sequence. We keep getting new steps in the graph sequence like we did before. And we can make an exchangeability assumption, as we did before, only now instead of node exchangeability, instead of exchanging the nodes, we'll exchange the edges. And so just as before we thought of this as, you know, maybe we could relabel sort of the people within the graph, here we can think of this as, you know, maybe these emails are coming in time, and we think, hey, if I had seen these emails in a different order, maybe that shouldn't change my analysis of this Enron email database or something like that. And the way we'll encode this is very similar. We'll say that, as before, if we take a step out of the graph sequence, that the probability of that step wouldn't change if we had seen the emails in a different order, if we had seen the edges in a different order. And the reason that we're going to keep talking about this at all is that we can show that, in fact, a wide class of edge-exchangeable graph models do yield sparse graph sequences, unlike node-exchangeable graph models. Okay, so to go forward, we'd like to sort of better understand edge-exchangeable graphs. I mean, for one thing, it seemed like it was super useful to have this characterization theorem for node-exchangeable graphs. In fact, we were able to use this Aldous-Hoover theorem to prove all kinds of things on, well, really the main thing, this density theorem, this density corollary about the node-exchangeable graphs. And so it would be nice to have a similar characterization theorem for edge-exchangeable graphs. And then also we'd like to say a little bit more about this sparsity theorem for edge-exchangeable graphs.
So like, what is the definite conditional variable?
Exactly, exactly. So this is essentially saying what is, you know, the Di-Finetti theorem, although there are other types of characterizations that we might have. So one way to think about it in terms of things we talked about before, the Di-Finetti variable would be something like the Dirichlet process, and there are other types of characterizations that I'll start by talking about that are more like the marginal or the Chinese restaurant process. And then two, this will just be showing that we can achieve sparsity. Okay, so let's start with this characterization theorem. And if you were at the tutorial this morning, you'll hopefully find it useful because was that a question in the back there? Oh, okay. So you'll hopefully find it useful because it turns out we're going to use a lot of ideas from clustering to show this. So remember that clustering is where we want to find this hidden, meaningful, latent structure, and that structure has a particular form. Each data point belongs to one and only one group called a cluster. Now again, we want this to be meaningful. So we'd be very pleased to find after the fact that if our data points were in fact pictures, that all of the pictures of cats were in one cluster and all of the pictures of dogs were in one cluster, et cetera. Now another way that we can represent a clustering is in a matrix-like form. I say matrix-like because there's no real order on the columns, there's no real order on the clusters. But here we can see that pictures 1, 2, and 7 belong to a cluster, pictures 3 and 5 belong to a cluster. And the relevant grouping here, what we're seeing in the columns, are the clusters. And here we have, if we're interested in exchangeability, the relevant form of exchangeability that people would typically talk about is the one that I mentioned earlier, that if I downloaded these pictures from the internet, I don't think that the order I stored them in my hard drive really matters. I think that I could have seen them in a different order, processed them in a different order, and it shouldn't change the distribution. Now, what I like about this representation is it's clear that something is missing for some types of data analyses. What if I have a picture that has a cat and a dog, or a cat and a dog and a mouse? What do I do then? In this case, I might want a more general version of clustering called a feature allocation, where data points can belong to multiple groups at the same time. In this case, the groups, these columns, will now be called features instead of clusters. The underlying grouping will be a feature allocation instead of a clustering, but the notion of exchangeability is the same. I still say, hey, I downloaded these pictures off the internet, and I don't think that anything should change if I permuted them. Yes?
Is it common in clustering algorithms for them to be exchangeable?
Yeah, so it's very common for an exchangeability assumption to be baked in. I would say that it's less a property of the algorithm as it is of the model. So for instance, in something like a mixture model, you'll find that it is typically the case that if I had permuted the order of the clusters, that it wouldn't change. So for instance, if I'm doing something like I say, here are the probabilities of my clusters, and I'm going to draw the assignments of data points to clusters from those probabilities, then and then my data will depend in some way on that, then typically the exchangeable part comes in basically because I'm always drawing from the same distribution. And so that kind of serves as a Di-Finetti mixing measure for clustering.
So the model for the data is once you've chosen all the Bayesian parameters, the data are IID. So that's,
exactly. I mean, exchangeability, basically the Di-Finetti's theorem is that data is conditionally IID, conditional on this underlying parameter.
that's where the exchangeability
Yeah, exactly. And so this is a great point that basically it's baked into most Bayesian hierarchical models because you're making that conditional IID assumption. Yeah. Okay, so here's the thing. Why would we care about clustering and why would we care about feature allocations? Because you can think of these edge-exchangeable graphs as being a specific case of feature allocations, where now if we think of our data points, because these are the things coming in one at a time, as being the edges, and we think of our groups as being the nodes, so maybe instead of cat, dog, mouse, you could think of this again as like Alice, Bob, etc. But if you think of it this way, then this will generate a graph so long as each edge, each data point, belongs to exactly 2 nodes. So it's like a special case of a feature allocation where each data point belongs to exactly 2 features, just as a clustering is a special case of a feature allocation where each data point belongs to exactly 1 feature. And now the groups, the columns, are the vertices instead of the clusters or the features. And the relevant notion of exchangeability, where we exchange the rows, is exactly edge exchangeability that I said earlier. And so if we know something about feature allocations, it seems like we should be able to say something, therefore, about these edge-exchangeable graphs. Just to illustrate how we build up an edge-exchangeable graph in this way, I'm just going to color each of the nodes for the purposes of illustration. So here we would have our first edge, which would be between the sort of red and the yellow node. We get a second edge with the green node coming in. We get another edge with a new node that we haven't seen before. Here's a new node. Here's an edge that we have seen before, so we're allowing some multiplicity in edges here. And we just keep building up our graph in this way. Okay, so this suggests to us that it might be profitable to look at clustering and feature allocations in order to apply that theory to edge-exchangeable graphs. So edge-exchangeable clustering has been very well studied. There are lots of characterizations of what happens, what sort of distributions are even available to us, what properties do they have. And that hasn't been the case historically for feature allocations, much less edge-exchangeable graphs. And so we'd like to say, can we take this theory and apply it here?
So you want every data point to get exactly 2 features?
So in this case, in the edge-exchangeable graphs, that's the first thing that you could do. You could then go on to think about hypergraphs. You could think about self-loops. You could think about skips. But that would be the basic case. It'll turn out that basically all of those things I just described are contained in feature allocations. And so it's actually really easy once we have feature allocations under our belts.
So it's not a big deal to specialize it.
Yeah, exactly. So the part about this really belonging to just 2, an edge belonging to just 2 nodes is not important to what I'm describing. Yeah. Okay, so let's talk about what do we know about clustering? What actually is known? Well, here's one thing that is known. Suppose that I take a clustering. So here I have n data points, and they belong to k clusters. And I look at the probability of that clustering. And if this, in fact, this random clustering is exchangeable in the way that I described before, if I'd seen the data points in a different order, it doesn't matter, then there can always be found some function p that's symmetric in its arguments, and the arguments are the sizes of the clusters. What's the size of the cluster? The size of the cluster is the number of data points in that cluster. So here the size of the kth cluster is 1, the size of the first cluster is 3, and it's symmetric function because there's no ordering on the clusters. So I could have permuted them and nothing would have changed. Okay, so when this exists, and it's been shown that it always does for exchangeable clustering, it's known as the exchangeable partition probability function, or EPPF. And one of the reasons that it's important in clustering and that it's a nice thing to have is because it's actually really useful for things like Gibbs sampling. So this is actually really intimately related to the Chinese restaurant process, for instance, if you're familiar with that. And so a first question we might ask is, hey, is there a similar characterization for feature allocations, and thereby for graphs? Well, first of all, let me just say that a completely equivalent thing that we could have done is we could have said that this is a function symmetrically of the sizes of the clusters and of the number of clusters. That would just be redundant because, and of the number of data points. This would just be redundant because the number of data points is equal to the sum of the sizes of the clusters and is therefore itself a symmetric function of the sizes of the clusters. Now, this is more important for feature allocations. So if we say that, hey, let's define an exchangeable feature probability function. We'll just define that, and we'll say that the probability of an exchangeable feature allocation, if it has an EFPF, if it's a function of the number of data points and then a symmetric function of the sizes of the features, where again, each feature size is the number of data points that belong to that feature. Now, this is important to include the number of data points because it's not a symmetric function of the sizes of the features. I could have 10 data points and 0 features. I could have 100 data points and 0 features. These aren't intimately connected anymore. Well, we show in previous work that, in fact, unfortunately, there are some distributions, in fact, very common ones, things like the Indian buffet process, if you've heard of that, that have EFPFs, this nice form that's useful for Gibbs sampling, but there aren't all. the exchangeable feature allocations have them. So this isn't a characterization of exchangeable feature allocations. So that's too bad, but what about graphs? Well, we can imagine defining a similar function for graphs. Again, here the data points are now the edges and the groups are the vertices. The size of the feature is the number of edges that belong to the feature. So there's a more common name for that in graphs. It's the degree. It's the size of the vertex. It's the number of edges that belong to the vertex. That's just the degree. And this dependence on the number of data points is again sort of superfluous because actually we can get the number of data points by summing up the degrees and dividing by 2. So this makes us think, hey, maybe this will work out. Maybe there will be some characterization of this form for edge-exchangeable graphs. This thing that we might call the exchangeable vertex probability function. And in order to see that that in fact is not true, let's go through a simple example. So remember, if something had an exchangeable vertex probability function, its probability would be a symmetric function of the degrees. Okay, so here is an example. Imagine that we just have a very simple graph. It's just on 4 vertices. Or sorry, it's just on 4 vertices, and in fact, we're only even allowing 4 possible edges. So we'll allow this edge, this edge, this edge, and this edge, and then they just repeat. And that's it. That's the only thing we're allowed. And we're going to make a very simple model for this where we say that the probability of one edge is P1, the probability of this other edge is P2, and each probability of an edge is stated here. It's all between 0 and 1. These are numbers that add up to 1. Okay, well, if an exchangeable vertex probability function existed for this model, it would have to be that these 2 graphs would have the same probability, because it only depends on the degree, and each of these has 4 vertices, each with degree 1. But we can find the probability of each of these graphs. So this graph has probability of this edge times this edge. That's P1 times P2, which we get from up here. This graph has probably this edge times this edge. That's P3 times P4. We can easily choose numbers between 0 and 1, P1, P2, P3, P4, that add up to 1, but such that these are not equal. And so this does not have exchangeable vertex probability function, but it's pretty obviously an edge-exchangeable graph, because all I had to do was independently and identically choose one of these edges every time. And so I could easily permute them and just have the same probability. Okay, so if we're trying to find an edge-exchangeable characterization, this is not it. We've shown not only that not every edge-exchangeable graph does not have an EVPF, but in fact every edge-exchangeable feature allocation does not have an EFPF, since this is a special case. Okay, so if we go back to edge-exchangeable graphs, we sort of now know that the graphs with exchangeable vertex probability functions are a strict subset of all edge-exchangeable graphs. And we need to go back to the drawing board and think about what other characterization theorems are there. And I think really the sort of straightforward thing that we would have thought of is let's look at the Di Finetti mixing measure. And so again, let's go back to clustering and say, what do we know about clustering and how can we apply it here? Okay, so clustering. Here's a way to generate an exchangeable clustering. Let's take the probability mass from 0 to 1, and let's partition it. So here I happen to partition it into 6 elements, but it could be any number of elements. It doesn't have to be 6. It could be a random number of elements. It could be a countable infinity of elements. And the partition intervals themselves could be random. Okay, so now what I'm going to do to generate my exchangeable clustering, or to generate my clustering, is IID uniformly at random. I'm going to put down a uniform random variable for each data point. So for the first data point, I put down this uniform random variable. For the second data point, I put down this uniform random variable. And when 2 of these uniform random variables fall into the same bin, I'll say that these 2 data points belong to the same cluster. So data points 1 and 2 belong to the same cluster. Data point 3 forms a new cluster. Data point 4 forms a new cluster. 5 belongs with 3, and so on. And hopefully it's clear that this generates an exchangeable clustering, because if I permuted any 2 of these IID uniform random variables, which are independent from this construction, this partition, then I'm not changing the distribution of the clustering. And what Kingman showed in 1978 is that the converse is true. So this is the really powerful direction. If I have any exchangeable clustering, then it must have a Kingman paintbox representation like this. An example of this would be something like a Dirichlet distributed set of probabilities or a Dirichlet process distributed set of probabilities, but it doesn't have to be that. It could be much, much more general. Okay, so why is it called the Kingman paintbox? Well, you can imagine that there's some color associated with each of these partition elements, and that the data points pick up the color of the partition into which they fall. And this isn't just fanciful. You can actually think of that color as being some parameter associated with each of those partition elements. So if I'm actually making a full generative model for my data, then the data points that fall into one of these partition elements, will all be pictures of cats, or the data points that fall into another one will all be pictures of dogs, etc. Okay, so what I'm going to do here is I'm going to show you the exact same model. I'm not changing anything at all, except for the way that I depict it. So the only thing that I've done is I've separated out each of these partition elements onto its own level. But I'm still doing the same thing. I'm saying when I make one of these IID uniform random draws, it belongs to all the groups that it intersects, and it intersects one and only one group because these were mutually exclusive and exhaustive partition elements. So this data point belongs to the dog cluster. But now it's clear that there's a natural generalization. What if instead of mutually exclusive and exhaustive elements, I in fact had more general subsets? Now these will correspond to features because when I put down an IID uniform random variable, it could intersect multiple of them, it could intersect none of them, it could intersect one of them. These are all possibilities. So again, we could play the same game. We could say, hey, I have all of these subsets of the unit interval now. When I put down my IID uniform random variables, they correspond to my data points. This one belongs to two features, and that's fine. This will be like a picture that is of a cat and a mouse. And then I put down my another IID uniform random variable. This one belongs to no features, and that's fine. This one shares one feature with data point 1, and so on. And again, we see that this is going to generate an exchangeable feature allocation, because if I permute any two of these IID uniform random variables, I don't change the distribution of the feature allocation. And what we show is that the converse is true as well, that if I have any exchangeable feature allocation, then it must have this feature paintbox representation for its distribution. And so finally, it's pretty straightforward from here to say, what's going to be the Definetti mixing measure, essentially, for edge-exchangeable graphs? Well, now let's just restrict this so that each data point can only belong to 2 nodes. And so now when I put down my IID uniform random variables for each of the edges, so I put down this edge, it intersects these 2 nodes, and so I generate this edge. I put down this edge, it intersects these 2 nodes, and so I get a new node. I put down this edge, it intersects 2 nodes I've seen before, so I get an edge with multiplicity. And I can keep doing this. Put down another edge, I get 2 nodes I haven't seen before. I get a new node here, and so on. And again, we see that this generates an edge-exchangeable graph. If I permuted any 2 of these IID uniform random variables, independent from now what we might call this graph paintbox, I'm not changing the distribution of the graph, and so I must have an edge-exchangeable graph. And then, of course, the converse is true. A graph sequence is edge-exchangeable if and only if it has this graph paintbox. And as we mentioned earlier, this extends to hypergraphs. By just, again, looking at the feature allocation, we could have some edge connect to more than 2 vertices. It extends to self-edges if we have an edge that just connects to 1 vertex. And we can have skips, even. So if you just don't have an edge on a particular time, like if these really represent time periods for you, it might be important to just have nothing happen on that step. Okay, so we now see that the edge-exchangeable graphs are the graphs described by graph paintboxes. So check, we have this characterization theorem for edge-exchangeable graphs. And it just remains to show that there exist sparse graphs within this edge-exchangeable framework. And so let's think about how can we prove sparsity. Well, remember, density and sparsity are defined when the number of nodes goes to infinity. So we're going to have an infinite collection of nodes, but we saw earlier that we can do this sort of thing with nonparametric Bayes. And so in particular, we're going to have a countable number of latent nodes, just like we had a countable number of latent clusters in the tutorial. So just imagine that this sort of goes off to countable infinity. And we're going to take an idea from some previous papers of having a graph frequency model or vertex popularity model, by which I mean we'll have a frequency for each of the vertices. You can think of it as a popularity of the vertex. So we'll just assign this for every one of the vertices. And we've already seen things like Dirichlet processes in the tutorial, so this doesn't seem too crazy that we could do this, that we could generate this infinite collection of popularities. And then we're going to draw edge ij with probability wi, wj. Now, I want to emphasize, here we're just trying to show that you can get sparse graphs. So we're not describing all possible edge-exchangeable graphs as we were before. We're saying here's a subset, reasonably large subset, where you can get sparse graphs. And so it's not just any graph paintbox anymore. It's a specific type of graph paintbox where we have a countable infinity of these layers. Each one has total mass proportional to the vertex popularity. And then the intersection size is proportional to the product of the two vertex popularities. Now, if we do this, if we make all of these choices, then we just need to make an additional assumption that the w's decay at the right rate. So one of the questions I got in the tutorial was, what if I want to have a logarithmic growth or a power law growth in my number of clusters? And it turns out basically that there are things beyond the Dirichlet process that let you get growth that isn't just logarithmic. So Dirichlet process will give you logarithmic growth, but things like a Pittman-Ure process will give you power law growth. And so there are basically things that we can make that let us have power law growth. And now I'm going to describe this just in some math, but essentially all of this part is saying is, let's take one of these processes, let's assume it has the right tail behavior, this power law growth tail behavior. If we do that, then we can get the number of vertices grows almost surely basically like n to the alpha, and the number of edges grows almost surely like n. And so if we choose alpha appropriately, basically between 1/2 and 1, we're going to get sparsity. We can also look at a binarized version of this. So remember, we had this multiplicity in edges. We could say what happens if we just treat any multiplicity of edges as just a single edge. So as long as we have one or more edges, that's a single edge, and we can get a similar result there. But the real point here is that for this very wide class of graphs, we can, in fact, get sparse graphs.
You can get any exponent between. It's nice.
Yeah. Oh, was there a question?
You kind of went quickly over the part where you did the paintbox, the two-color paintbox.
Yeah.
You mentioned two constraints that you need. One is that the length of the total length of each color is given by wi.
Oh yeah.
And then the amount of overlap is the product of the wi's. Is that easy to show that it's even possible?
Yeah, so actually, this part's really the easy part. So it's really just that you're taking the probability and multiplying them. If anything, the graph paintbox is sort of this additional thing where you can show that you have this graph paintbox and you can make this construction. But really the way that you would generate this in actual, if you were simulating it or something, is that you would make these products of probabilities, and then you would use those as rates and generate from those.
So you don't have to worry about creating paintboxes with only 2 bars through
No,
every
yeah.
line or anything like that?
Yeah. It's more like you can make this construction and then you could show that this exists, but it's actually easier to go straight from the construction.
Okay.
Yeah. Okay. So we have this sparsity theorem. We know that sparsity exists in edge-exchangeable graphs. And so these were our 2 goals, to have this characterization theorem and the sparsity theorem. And it's worth thinking about, where these additional sort of groups or these sets fit into the Venn diagram. So we've shown that we can have sparse graph frequency models. But how does this all relate to this vertex probability function that we found from earlier? In the interest of time, I'll just sort of notice that the graph frequency models are a strict subset of all the graph paintboxes. We saw that it had this particular structure that you were just noting. And we noticed that the vertex probability functions have a particular strict subclass. And it turns out, in fact, these are the same. That the models that have these vertex probability functions are the same as the graph frequency models. Moreover, and then this is actually something that is very similar to a result more generally with feature allocations. Moreover, we saw that the sparse graph models were, we could show that at least some of the graph frequency models were sparse. It turns out that there are also sparse models out here as well. Okay, so there are a few things that I've glossed over here. So technically speaking, if we wanted to finish this up, there's a conception of dust that goes on here. So in clustering, this is like if you either have a probability of some cluster, and you'll see that cluster again and again as you get more data, or it's possible to have a cluster that occurs exactly once. There's one data point, it's sort of maybe an outlier, it belongs on its own, and then you never see that cluster again. And so there's a similar conception for features, for graphs, and for this extension of features traits. And there are a number of remaining questions here. Some are theoretical and some are practical. So on the theoretical side, can we characterize all of the sparse edge-exchangeable graphs? On the practical side, can we turn this into models and inference? Can we actually, this is very theoretical development, but now we want to choose particular, choices of the graph paintbox and use them in practice. And one thing that we've been doing in the Bayesian nonparametrics, more traditional land of clustering and feature allocations, is this idea of a truncation approximation for actually doing inference in Bayesian nonparametrics, and hopefully that can be applied in this graph realm as well. And so a few things I'll just highlight here are our paper from NIPS 2016 and some early work that appeared in a few peer-reviewed workshops in NIPS 2015. And then this more extensive paper, more recently that's on the archive and under review on exchangeable trait allocations. And this really gets into the theory of the characterizations and how to actually get these graph paint boxes and vertex probability functions and things like that. Thank you.